In this video, I'm going to talk about the Powerlaw model. The Powerlaw model looks like this. Y equals C, X to the B. There are two parameters, capital C and little b, that we have to find for every Powerlaw model. So that's similar to the exponential. That also has two parameters. The thing to notice here is that x is the base and little b is the only thing that's up in the exponent. Now, before we look at how to calculate these parameters for the Powerlaw model, I want to make a comparison. So let's take the Powerlaw model and the exponential model with the same parameters. Capital C equals 3.515 and little b equal to 2.136. So the Powerlaw model will look like this. Y is equal to 3.515 times x raised to the 2.136. And the exponential model looks like this. 3.515 times 10, and up in the exponent is 2.136x. So we want to evaluate each of these for x equals 10 and make a comparison. First, the Powerlaw model. That's going to be 3.515. I'm going to take 10 and raise that to an exponent of 2.136. Get that on my calculator and then multiply by 3.515 and I get 480, and I'll round it to two decimal places, so 480.76. Now the exponential model with those same parameters, we're going to see a big difference here. 3.515 times 10, and I'm going to raise that to 2.136 times 10. So that'll be 3.515 times 10 raised to the 21.36. The exponent is 21.36. And our final answer, let me squeeze it over here, 8.0523, I'll round it to there, times 10 to the 21. Huge, compared to a little 480 on the Powerlaw model with the same parameters. Okay, let's take a look at how we're going to calculate the parameters here, capital C and little b. This is going to be very similar to what I did with the exponential model. I'm going to take the log base 10 of both sides and then simplify using the log rules. I'm going to end up with a linear equation, and that will tell me how to proceed with the calculation. So the left hand side, log 10 of y, this is the same thing that we had with the exponential, and I know I'm going to be modifying my data set because this variable is no longer y, it's log base 10 of y. On the right hand side we have a product, and so that is equal to the sum of logs. The log of x to the b is the same as b times log of x. That comes from the multiplying exponents rule. This b comes down in front as a factor. And what I'm seeing right here is a linear equation. I have log 10 of y, that's my variable, and log 10 of x is the other variable. And I have C1 plus C2 times log 10 of x. So if I can find this line on the data set, log of x, log of y, I can find C1 and C2 and translate them back into the two numbers that I need for my Powerlaw model. C1 is log 10 of capital C. It's the same thing that we had in the exponential. To find capital C, I'm going to have to take C1 and put it as an exponent on 10. C2 needs no adjustment. That's going to be equal to little b. So once again, this is called the linearization of the data set. I'm looking for a Powerlaw model. I reduce it to a problem of finding a line, finding the y-intercept and the slope. And from those numbers, I can find my parameters. So let's take a look at a problem here. We have the length weight measurements for lake trout, and I want to find a Powerlaw model for this data set. The length is in inches and the weight is in pounds. I'll be able to use this model to approximate the weight of any lake trout if I know what the length is. So the x is the length of the fish and y is the weight. I'm going to be using log of x and log of y rather than x and y themselves. With the new modified data set, I'm going to find a line and then I'll translate those back to the parameters capital C and little b. Now, rather than calculate the log of each of these numbers and filling out a whole new row in my table, I'm going to let MATLAB do that. And same goes for the y. Rather than calculating the log of each of the y values, I'll go ahead and type the y values into MATLAB and let MATLAB calculate the logs. Then I'll form my matrix equation in the usual way and do the least squares calculation. In my matrix A, I'm going to have 1 and then the log of my first x value. Next row is 1 and the log of the second x value. So that's the only difference here. With this Powerlaw model, instead of using x's in my second column, I'm going to use the log base 10 of the x value. And on these two matrices, A and log y, ly, I'm going to go ahead and do the least squares fit. So let's go to MATLAB and take a look at how that works. I'll start out by typing in the matrix A. First column is going to be 1s and the log 10 of the first x value. And each row after that is going to be, I'll go ahead and copy this and make it a little bit easier to type in. I'm going to go ahead and put 1 and then the log base 10 of the x value. Next one is 20.5 and the next x value is 24.5. The next value is 30.5. And 38.5. So there's my matrix A, and the y values I'll type in directly, and then in a second step I'll take the log base 10 of each of those. The matrix Ly will be the log 10 of y. And again, it's important to remember to put that 10 there, to use log base 10 rather than another base. I'm now going to find the line using the least squares formula. Okay, so this line now is using the data set log of x, log of y. And I get my two numbers back again. Little b is the second one without any modification. And capital C, the other parameter, is going to be 10 raised to c of 1. That first number is the log base 10 of c. And so I can find it by putting that exponent on 10 and getting my value. So now I have my model. Capital C is very small, and let me go ahead and type the model in here. It's going to be 0.0000194 times x to the 3.1804. The model that we just found in MATLAB, let me write that down here. This is capital C times x, and the exponent little b is 3.1804. So that's somewhere between a cubic and a fourth degree polynomial. We can use this model now to estimate the weight of any lake trout in particular that we know the length of. So for this part B, for this problem, we're looking at using 32 for x. And what I'm going to do is put 32 right in there for x and raise it to an exponent. And here's my calculation from MATLAB. I have the coefficient already stored in capital C and the exponent in little b. And I end up with a weight of 11.8787 pounds. And notice that fits right in there to my data set. It's between 30.5 and 38.5 of length. That's where 32 fits in. And this weight fits in between those two values there. So it seems reasonable for this model.